welcome back. In this lesson, we're going to take a look at using a normal distribution, which we learned back in Unit 1, which is for continuous data, and we want to see if we can use it to approximate things that are binomial distributions. And you might be asking yourself why. Trust me, you will understand by the time this lesson is over why we want to do this approximation. The biggest thing that I want you to understand from this, though, is that binomial distributions in themselves are discrete data. They jump from one value to the next. They're what's represented in that picture there by the bars. Now, I will point out that that bar diagram is a little bit incorrect. Those bars should not be touching, but I didn't make the graph, and it's useful for our purposes. So the bars represent the binomial distribution, and the curve on top of it represents a normal distribution. And you'll notice that the curve and the shape of the bars is actually fairly similar to each other. So let's do an example where we say that this graph represents 10 coins being flipped, and each bar represents the probability of getting that number of heads. So for instance, if we look at this one right here, that bar represents the probability of getting 4 heads, and so on. So if we look at this as a picture, leave the math out of it for a second, just try and think of it as a picture. The left graph is actually the value that we get from a binomial distribution. That's the probability that the number of heads in this case equals 4. And since the height of each of these represents a percentage of a whole, if I added up the heights of all of those different bars, really the volumes of each, or sorry, the areas of each of those bars, because they're all one wide, you'd get a total of 100% of data. So 4 represents a certain portion of that total. The answer is around 20%. I think it's actually about 20.5% to be exact, but it represents about 20% of the total. So it means there's about a 20% chance that you're going to get 4 heads. So that's the actual precise answer. Now, if I go over to the right side picture, what it's showing there is the area between 2 points, and it's basically the area under the graph. So this is the normal distribution. And you'll notice that the area under the graph between those 2 points is very close to the area of the bar in the left graph. There's a little bit missing in the top left of the bar, but there's a little bit extra above the top right of the bar. And the idea is that those areas of the black shaded areas on these 2 diagrams are not identical, but they are pretty close to each other. So here's the key trick though. When it comes to a normal distribution, we can't just say what's the probability that there are 4 heads, because you recall that with continuous data, which is what normal distributions are for, it's impossible to get an exact value of 4 as a continuous number. We can do numbers, percentage of data above, below, or between 2 points. That's it. So here's where we're going to fake it a little bit. We're going to pretend that the number of heads is continuous data. I mean, that's kind of ridiculous that we could get a continuous number of heads flipped when we're flipping coins, but we'll pretend that it's continuous. Then what we really want to do is look at the probability that we get between 3.5 and 4.5 heads. And the reason we're doing that is because that represents the 2 sides of the bar for 4 heads. So basically we're just saying, let's go half below and half above, and anything between those numbers is going to round to 4, and that's going to give us the approximation. So for binomial, we have to use probability heads equals 4. For the normal distribution, we're going to do the probability that heads is between 3.5 and 4.5. Now, some of you may say, well, should those be less than, or should they be less than or equal to? And the answer is, I don't know, I don't care. Because remember that there is 0 probability of it being exactly 3.5 or 0 probability of it being exactly 4.5. So whether you're talking about less than or greater to, less than or equal to, or strictly less than is irrelevant. It doesn't change any of the math. So either way you want to write it is fine by me. So that's the idea of the trick behind it. If we can work a little below and a little bit above, we should be able to use the normal distribution to find the probability of something happening, even if it is discrete data. This leads us to one other little issue, and that's when we're dealing with binomials, binomial distributions, we talk about things like number of trials, probability of success, probability of failure. Those are the kinds of variables we need to solve binomials. And when it comes to normal distributions, we work with numbers like z-scores and x-bars and sigmas. Well, as it turns out, we can actually figure out what variables to use, or what values to use for our variables for a normal distribution using the variables from the binomial. So remember that n is the number of trials, p is the probability of success, q is the probability of failure. So that was the binomial stuff. And if we want to convert it over, we can say that the mean x bar is equal to np. Well, recall that x bar is essentially the same thing as expected value, which is np. So that one makes complete sense. And the standard deviation is the square root of n times p times q. Now that one probably doesn't make sense to anyone, but it does work. I'm not going to prove it, but just trust me right now, you can use that equation and it will work just fine. If you want the standard deviation of your data set, just take the square root of n times p times q. So you may recall back in the hypergeometric lesson, we talked about using binomial distributions to approximate hypergeometric, and that seemed to work as long as the pool we were drawing from was large enough so that the things we took out of it essentially didn't change it very much. So if you're taking 3 marbles out of 1,000 marbles, it doesn't change things too much, whereas if you're taking 3 out of 5 marbles, it makes a huge difference. So in much the same way, we kind of have a rule on how to determine whether or not our normal approximation of the binomial will be good. And it's basically just that NP and NQ must both be greater than 5. Why is it 5? That's the number that seems to work. Again, it's an approximation, so technically it always works. It's just how well it works. Now I need to point out that when you're looking at NP and NQ, it's going to be the lowest one that is really the weak link in the chain. So let's say that NP is 1,000,000. Well, that's awesome. That's much greater than 5. But NQ is 3. Then you're going to get kind of a lousy approximation. If both of them, NP and NQ, are both like 4.8, go ahead and use it anyway. It just means that it's not going to be a fantastic approximation, but it'll still work pretty well. But our general rule of thumb is that we want NP and NQ to both be greater than 5. If they're both much bigger than 5, it'll probably work really well. And if one of them, the lower of the two, is a little bit below 5, it'll probably be okay. If it's much below 5, don't even bother. So that's our rule of thumb. Okay, so going back to the things that we had pictures for at the beginning, that was flipping 10 coins and looking for heads coming up. Let's find the probability that exactly 4 of the coins come up heads, and we'll use the binomial distribution. So this is actually going to give us the exact proper answer. So the probability that heads equals 4. Remember, the equation for this is just we have 10 things. We choose which 4 of the 10 trials is going to be successes. And then we have probability of success, which is getting ahead. It's just 50% or half to the number of successes, and probability of failure to the number of failures. Okay, so plugging that into the calculator, that's 10 choose 4. And then I could write, or I could put in 1/2 to the exponent 4 times 1/2 to the exponent 6. That's just 1/2 to the exponent 10. Or I can divide by 2 to the exponent 10. And when I do that, I get out 20.51%, give or take. Okay, so before what I said, the bar was about 20%. Well, that's the exact number. That bar represented 20.51% of the data. So now let's try to do a normal approximation on this, but we should start by just making sure that NP and NQ are both at least 5. So in this case, NP, well, we have 10 trials, probability of success is a half, that's equal to 5. And NQ is 10 trials, probability of failure, which is a half, is also equal to 5. Okay, so these both of them meet the bare minimum to really use this approximation half decently. And I specifically chose it that way to show you that this is about as bad as the approximation will be as long as NP and NQ are both equal to 5 or big or more. Obviously, the higher they are, the better approximation will be. Anything lower than this, the weakest link is going to mess things up a little bit. So let's find the probability of getting 4 heads using a normal distribution. Now I'm going to do a little bit of an aside here. Specifically, I'm going to find x bar, which is equal to n times p. Now the nice thing is we actually just calculated that in part B. So that's our average. And then our standard deviation is the square root of NPQ. So 10 times a half is the square root of 2.5, which is 1.58. Now, unfortunately, we're doing an approximation of an approximation since we're rounding that off to 2 decimal places, but that's okay. I'm going to show you that even with a little bit of extra rounding and a weakest possible criteria being met, we should still get a pretty decent answer. Okay, that said, we're looking for the probability that heads is between 3.5 and 4.5, and again, it doesn't really matter whether you use less thans or less than and equal to, it has no effect on the math. And so what we do is we set up our z-score equations. So z is 3.5 minus the average, which is 5, out of the standard deviation. And the other one is 4.5 minus 5 over the standard deviation. Okay, so the first one is negative 1.5 divided by 1.58, which is negative 0.95 as our z-score. And then the other one is negative 0.5 over 1.58 is negative 0.32. Again, if I'm rounding properly. Okay, so we rounded once, we rounded twice, and we're going to put both of these roundings into our approximations. So this is approximated from every possible place. But let's use our z-score tables to look those up. So negative 0.95 is 17.106%. And negative 0.32 is 37.448%. And since we're doing percentage of data between 2 points, let's just do big percentage minus small percentage. And when we do that, what do we get? 37.448 minus 17.106 is 20.342%. Okay, so that's our normal approximation. Going back up for just a second, the exact value when we did it properly as a binomial was 20.51. Our normal approximation is 20.342, keeping in mind that we had the lowest possible bar to be met with both NP and NQ equaling 5. We rounded off on sigma. We rounded off on z-scores. Our z-score tables, obviously those percentages jump in values because it doesn't have a continuous spectrum. It just has boxes that we choose from. And we're still only off by very little. So I would say that that's a pretty good approximation. And I mean, let's be honest, in most situations, we would just say there's like a 20% chance anyway. We would already be rounding off. So our normal approximation here, I think, worked extremely well given how many parts of it were approximations. Let's try another similar question. A hospital has 50 babies born on a given day. We want to know how many are girls. Let's start off by seeing if the normal approximation will work. So remember, normal approximation should work if NP and NQ are both at least 5. Here we have 50 trials, and there's a 50% chance of being a girl. And then NQ, 50 trials, 50% chance of being a boy. Okay, both of those are much larger than 5, so we are good to go. Part B, use the binomial distribution to find the probability that exactly 20 of the babies are girls. Okay, that sounds pretty easy. Probability girls equals 20. And that's just 50 trials, choose 20 successes. Ladies, congratulations. Girls are a success in this question. Boys are failure, but only mathematically. You're all special, beautiful people. 50 choose 20 tells us where the successes occur, probability of success to the number of successes, probability of failure to the number of failures. Okay, so punching that into the calculator, 50 choose 20, big number, divided by 2 to the exponent 50, and I'm getting out, again, normally I'd probably round this off, but just because I want to compare the normal approximation to the binomial approximation or binomial exact answer, I'll keep a few extra digits. So 4.1859%. In fact, you know what? I think I'm going to specifically round off to 3, and the reason for that is because that's what our z-score table will give us. 3 decimal places. And again, getting it exact is almost impossible from the z-score table unless that exact value shows up in the z-score table, and I don't believe it does. Then again, I didn't look. 4 point, yeah, I don't know if it's there. Yeah, my eyes are all over the place. I think I see a 4.182 is the closest I could get from the table. Now let's use a normal approximation to find the probability of exactly 20 of the babies being girls. Now, before we go too much further, I want you to look at the binomial answer and realize that that was actually really easy to come up with and is exact. So that's the way I would go if I was solving this problem. But let's do what it says and try to use the normal approximation. So again, off to the side, I'm going to say x bar equals n times p. And again, we already did that in part A. Kind of one bonus of making sure that we can use it is that we already have calculated one of our things. Again, makes complete sense. If you've got 50 kids, you'd expect an average of 25 of them to be girls and 25 to be boys. Sigma is equal to the square root of n times p times q. Okay, so that's 50 divided by 2 divided by 2. Square rooted is 3.54. 5355. Yeah, we'll round off to 54. Okay, so if you don't want to write out the notation like we did last time, the probability that, actually, you know what, I should just to remind you why we're doing what we're doing. With this distribution, of course, this is normal distribution, so it has to be continuous data. We're not looking for the probability that girls equals 20 because it's impossible. If the data is continuous, we're looking for the probability that it's between 19.5 and 20.5. Because as continuous numbers, anything falling between that would round off to a whole number of 20. Okay, so much like last time, we set up our two z-scores. Z equals 19.5 minus 25 over 3.54. and the other one will be 20.5 minus 25 over what, 3.54. Take a moment to punch that into your calculator. And this one is negative 1.55. And the other one is negative 1.27. Okay. So let's look up those probabilities on our z-score table. Again, not equal signs, just corresponding percentiles to those z-scores. Negative 1.55, I'm getting 6.057%. And negative 1.27, negative 1.27 is 10.204%. Okay, and since we're looking for data between, we do subtraction of the big one minus the little one. And when we do that, 10.204 minus 6.057 gives us 4.147%. Compare that to our answer up here, which is the exact answer, and that's pretty close. That's pretty good. So then the question becomes, if part B was the correct answer and was easy, and part C was the approximate but wrong answer and was hard, why would we ever do it that way? Let's see if, just read question D and see if we could figure out why that might be. Use a normal distribution to find the probability that there are at least 15 girls. Okay. If we do this one directly, we have to do the probability that there's 15, 16, 17, all the way up to 50 girls. So we have to do something like we did in part B, but about 35 times. If, however, we do it the indirect method, we have to do 100% minus 0 to 14, I think. Oops, sorry, I did it the wrong way around. The direct method here is up to 15, so I would have to do 15 cases, and then the indirect method would be 15 to 50, which would be 35 or 36 cases. Either way, do we want to do 15 to 35, 36 binomial distribution equations? So when we've got a situation like this where we're doing a range of values, the number of values is the number of binomial distribution equations we have to solve. When we do a range like this using the normal approximation, it's going to be exactly the same amount of work as part C was. The numbers change, but the literal number of steps and number of things to write down is identical to part C. All that we do is replace the 19.5 and the 20.5 with different things. In fact, we can do this in a slightly different way, and I'll show you what I mean by that. So use the binomial distribution to find this. No thank you. By the way, you can't write that on a test for marks. This is the lesson though, and I'm the teacher, so I get to do what I want. But yeah, that would be way too time consuming. We'd have way too much to do, which is why I left such a small blank there. Now use the normal approximation to find the probability that there are less than 15 girls. This one you've got to be a little wee bit careful about. I'm going to draw a little diagram up here in the top, just because there's some room up here, not because it needs to be here. So if I do, there's a bar somewhere for 15 girls, and there's a bar for 14, and a bar for 13, and so on. If I want it to be less than 15 girls, that means that these bars here are the valid ones. 15 is not a valid bar because I want strictly less than 15 girls. That means when I'm doing my normal approximation, that's actually my breaking point, which is 14.5. So if I want to do a normal approximation, what I'm really following is the probability that the number of girls is less than 14.5. And so I do my z-score for 14.5. We already have the values for x bar and sigma there, 25 for x bar and 3.54 for the standard deviation, so no new calculations. Punch that into my calculator. And I get negative 2.966, but again, this is a z-score, so negative 2.97. And then when I look that up on my z-score table, negative 2.97, that's very close to the beginning, only represents 0.149% of data. Now I should point out that there's one thing, and it's so subtle that most students don't even recognize that it's happening. Back when we did this in Unit 1, when we did normal distributions, the percentage that we got was the percentage of data that fell above, below, or between 2 points. So we'd say things like, here's a whole bunch of whatever, here's a whole bunch of babies, or a whole bunch of days where they had 50 babies, 0.149% of days, they're going to have less than 15 girls. Now what we're going to do is we're still going to use that same mathematics, that same percentage, but now we're not thinking of it as percentages of the whole thing. It's actually the probability that a single day with 50 kids being born is going to have less than 15 girls. So Unit 1, the percentage was really percentage of all data points. Here it's the probability of a single data point. Interesting little difference, but like I said, mathematically doesn't change anything. It's just a subtle difference to recognize. Okay, so in this case, it actually worked out to be, well, easier actually than the original one, because the original one was between two numbers, and this one's just below a number. So it actually was only one z-score calculation instead of two. Now, I will point out that some people that I've had in my class before have pointed at something that is actually valid. I just tend to wave past it. And that's that they say, well, if we're thinking of these discrete numbers, shouldn't I really be looking at the number of girls being less than 14.5 but greater than negative 0.5? Because negative 0.5 is the last discrete number I can get. So should I be calculating it this way? Oops, sorry. Should I be calculating it as this, since those are the numbers that round to 0 to 14 girls? And the answer is you're welcome to do it and solve it the exact way that we solved number C, or part C, since C is not a number. What you're going to get is one of the two. In this case, I think you're going to see the percentage of data below negative 0.5. Negative 0.5, you're already like 8 standard deviations below the mean. It's going to work out to be a 0%. So what you're going to end up getting is, once you've done the work, you'll get 0.149% minus 0% equals 0.149%. So if you want to do it between all the time, you're more than welcome to. But once you've gone off the side, either left or right of this, you're going to be at 0% or 100%. If it's 100%, it's just the same case as when we do percentage above a number, which is 100 minus whatever anyway. So we only have to, in this case, since we're looking for less than 50, we don't have to kind of stop it at 0 girls. We can just pretend it goes forever, as long as it's less than 15. Okay. What is the probability that there are at least 20 girls? Now, again, I'm going to draw this little diagram because some students find it helpful to make sure that they've got the right starting point. I'm just going to draw a couple little these are completely arbitrary heights. I have no idea what they're supposed to be in height-wise. And I'm going to take the number that was given 20, and I'll do a number below and a number above, and make sure that I'm actually plugging in the right thing. So the probability there's at least 20 girls. 19, that's not enough. 20 is, so 20 is valid. 21 is valid. Anything higher is valid. So our breaking point on this one is going to be the 19.5. And I find that little diagram can be helpful just to help yourself understand where the breaking point needs to be, depending on the wording of the question. Test the value above and below the one given and see if they meet, if they kind of are the spirit of the question. Okay, probability that there are at least 20 girls. Again, we could say 19.5 up to 50.5, or we just say greater than 19.5. I think we're just going to do it that way. So that's 19.5 minus x bar over sigma. And that is negative 1.55. And this is looking familiar. We actually, I think, did this one earlier in the problem. And when I did that one earlier in the problem, oh yeah, here it is, right here. Negative 1.5, we got 6.057%. Okay. Now, if we were going to calculate it up to the 50.5, I want you to keep in mind, it's really saying what percentage of data falls below 50 girls. Well, 100% of data is going to be 50 or lower. It can't be more than 50 girls. So 50 girls or lower, that's going to be 100% of data, which is why this question, that's percentage below. To find the percentage of at least 20, we're going to do 100% minus this. So we don't need a z-score to tell us that that's 100%. We know it's going to be 100%. And so the percentage of data that will be above 20 is going to be 93.943%. And finally, let's do one where we do between two values. What is the probability that there are 15 to 35 girls out of 50? Now this one, again, I find the bar to be helpful. I want to point out that I'll do 14, 15, and then up towards at the top, we're going to have like a 35 and a 36. 14 is not a valid number. Now the wording on this may change it. If it said between 15 and 35, then technically 15 is not between the two. 15 is one of the end points. If there are three kids sitting in a row and I said who's sitting between the two on the end, no one would say, well, it could be any of the three of them. The ends don't count. But in this case, it says 15 to 35, so 15 is valid. 35 is valid, 36 is not, everything in between is. So our breaking points will be 14.5 and 35.5. Okay, so that gives us two z-scores that we need to work with. Z equals 14.5 minus 25 over 3.54, and Z equals 35.5 minus 25 over 3.54. So that first one is negative 2.97. And I think we actually just did that one too, didn't we? Somewhere? Yep. Negative 2.97 gave us 0.149%. And then this one is going to be positive 2.97. Makes sense that there's some symmetry here since 15 and 35 are both 10 away from the median. The mean. They're kind of symmetric. And you can look that one up on your z-score table, and you're going to get 99.851% of data. And that means that the probability of being between those two extremes of getting 15 to 35 girls is 99.851 minus 0.149, which is 99.702%, I think. So what is this telling us? If there's 50 kids born in the hospital on a given day, there is a 99.7% chance that the number of girls will be between 15 and 35. It's very unlikely that we're going to get just a few girls or almost entirely girls. Yeah, that kind of makes sense. We would expect some number closer to the middle since it's a 50-50 chance of anything happening. One last one to finish things off. Take a little change of pace away from our children in the hospital. A pair of regular six-sided dice is rolled 80 times. What is the probability that there will be at least 20 rolls where the sum is 9 or higher? Okay, there's a whole bunch of things going on here. First thing we've got is, could we do this using a binomial distribution? Because it is a binomial distribution problem. And the answer is yes. It's just that we're going to have 61 cases if we solve it directly, which sounds like a bad idea. And we're going to have 20 cases if we solve it indirectly. That sounds like almost as bad an idea. Actually, it sounds like 1/4 as bad an idea, but still a bad idea. So let's maybe try a normal approximation on this one. Just before I do that, though, NP in this case is going to be number of trials, which is 80, times the probability of success, which we actually currently don't know. So the first thing, I shouldn't say the first thing because apparently we already did the first thing. The next thing we should do then is figure out what that probability of success is. So what we're looking for is getting a sum of 9 or higher. That's where our dice table comes in. And I'm going to cheat again and not do the whole thing. But I am going to remind you that the bottom corner, the bottom right corner is 12. So that'll be the 12 there. And this will be the 11s, 10s, 9s. 12, 11, 10, 9. Yeah, that seems to work. Even if you're not writing out all those sums. And that's 10 of the possible outcomes out of 36, or 5 out of 18 in lowest terms. I could convert this to a decimal. I don't know if it really matters at this point. I guess for NP and NQ, we're going to have to eventually convert these to decimals anyways. So 5 out of 18 is 0.2777. I guess 0.2778 when I eventually cut it off. 77 repeating. Multiply that by 80, and we get 22.222. Now, if that's the probability of success, then the probability of failure, probability of failure would be 1 minus the 0.27 repeating, which is 0.72 repeating. And when I plug that into my calculator, by the way, at this point, I don't even need to punch that into my calculator. I can visually already see that Q is larger than P, and since NP is way bigger than 5, NQ is going to be even larger than that, but you know, just to humor the correctness of this, or the completeness of this paper, let's write down 57.78. Okay, so those are both significantly larger than 5. This is a good candidate for normal approximation. Next step, I suppose, would be figuring out what x bar and sigma are. X bar we already have, it's 22.22. Sigma is the square root of NPQ, which is 80 times, humor me here, I'm just going to write these in as fractions because it's easier than writing in the decimals with the amount of space I have. So probability of success is 5 out of 18. Probability of failure is 13 out of 18. Well, be slightly more accurate when I punch into my calculator as well. Times 13. Okay, so that's the square root of 16.04 something, which works out to be almost exactly 4. It's actually 4.006. I'll leave it like that. That's good. And then a couple other numbers, but that's close enough. So now the probability that at least 20 rolls works means 19 is not enough, 20 is. So I really need to do the 19.5 as my breaking point. So 19.5, anything greater than 19.5 will be at least 20 when I round it up to a whole number, or round off to a whole number. So 19.5 minus 22.22 divided by 4.006. $19.5 minus 22.22 divided by 4.006. And at this point, all of our rounding is going to kind of be washed away since we have to round this off to 2 decimals anyway. And it's going to round off to negative 0.68. Next step then is to look it up on our z-score table. Negative 0.68 is 24.825%. And then again, we're going to remind ourselves that this is the percentage of data under. And we're looking for at least 20 rolls, so we're looking for percentage of data over. And when we do that, we get 75.175%. So 75% of our, or there's I should say, in Unit 1, I would have said 75% of our data is over, 20 or over. In this unit, I'm going to say, doing this experiment once, rolling the dice 80 times, there's a 75% chance I'll have at least 20 rolls with a sum of 9 or higher. So pretty significant chance. Okay, so hopefully you've kind of caught the tricks and tips for this one. We're basically just doing normal distributions like we did in Unit 1. The difference is that we have to be very careful about how we choose our kind of starting and ending points, or at least our only point, our x values, because we have to do a discrete, which is usually a half above, half below thing. And we have to convert our NPQ variables into a x bar sigma variable. Other than that, pretty much the same. So I'll stop there. You can try some homework problems, and I will catch you in the next and final lesson of the course. Ooh, that's scary. Okay, we'll see you next time.